safe and robust observer controller synthesis using control barrier functions. My name is Devansh Agarwal. This work was in collaboration with my professor, Professor Dimitri Panagud. The main motivation of the work is the following. Consider this quadrotor flying around in this figure of 8 pattern trying to avoid a barrier over here. Even if we use control barrier functions or some other safety critical technique to be able to design a controller to avoid such a crash, because we need to provide a state estimate that is not the same as the true state of the system, our quadrotor could become unsafe. Consider this block diagram. Our system has some dynamics, but because we don't have access to the full state, we have to use sensors, and in fact noisy sensor measurements, to be able to construct a safe estimate x hat that is often passed into the controller. Because of the uncertainty introduced in the system, there is uncertainty in x hat, which could lead to unsafe behavior. So the effect of understanding the observers is critical to ensuring safety, and that is the main purpose of this paper. Let's provide a brief review of control barrier functions and how they've been used for safety. They've become a really powerful tool because they allow us to synthesize nonlinear safety critical controllers pretty much online. Here, we consider a control affine system, x dot equals f of x plus gu, subject to some bounded disturbance, g disturbance times d of t, where d of t is bounded and the bound is known a priori. We say a system is safe, or in fact a controller renders the system safe, if, for the safe set, any initial condition that the state starts in maintains itself within the safe set. So x of 0 in S implies x of t in S for all time in the future. In the context of control barrier functions, we suppose that a safe set is defined as the superlevel set of some barrier function h. And we say that h is a robust control barrier function for the system if there exists a class K function alpha such that at every state x there exists a controlled input such that h dot is greater than or equal to negative alpha of h, considering all possible disturbances that could be present at the current time. And supposing that h is a robust control barrier function, we can define a QP controller, a safety critical quadratic program controller, and it takes this form. We say that pi, the control output, is a control input that we choose, is decided as a argument of u with respect to pi d, where pi d is some desired control input. And this constraint is, in this QP is subject to the constraint, which says that h dot must be greater than negative alpha h. Now, when we introduce observers, we don't have access to the full state of the system, and in fact, we are only given access to some measurements y, which is given by some c of x, plus some disturbances, c disturbance times v. Again, we assume that the disturbances v are assumed to be bounded with known bounds. If we define the safe set as before, and we try and do the similar analysis from before, we'll notice that we have these terms x that show up in our QP controller. And since we don't have access to the x, we can't really implement the QP controller as is normal. In fact, visually, you see that we only have access to the state estimate and measurements y, and even if we keep the state estimate within the safe set, because there's some uncertainty of the state, the true state could lie outside of the safe set while the system is evolving. As is normal with classical linear systems theory, even if you have a stable observer and a stable controller, that doesn't mean you have a stable observer controller. Similarly, in the context of safety, even if you have a stable observer and a safe controller, that doesn't mean you have a safe observer controller. And this is the main focus of this paper, trying to develop these observer controllers. Let's put it a little bit more formally. Suppose we're given this affine control system, control affine system with subject to bounded disturbances. We're tasked to design an observer controller, and we assume the observer controller follows this form. It's control affine, and the control input has to be determined as a function of both the state estimate x hat and the measurements that are present at the current time y. We assume this control affine structure, and it's common across things like the Leuenberger observer or the Kalman filter. The second part of the task is to design initial condition sets x hat and x hat 0 such that x0 and x hat 0 that render the system safe. These initial condition sets are necessary because if you started the system at the boundary of safety, and if the state estimate lied within the boundary of the safety, if your true state lies outside, you can't guarantee safety. Similarly, you could have scenarios where your state estimate is such that as soon as you get a measurement, you think your state estimate has exited the safe set. So designing initial condition sets is important. The essential idea is that you need to start sufficiently safe to start with until the observer error is able to converge to the point where you're able to guarantee safety. So the idea is that somehow we need to design the initial conditions that ensure safety. There has been some related work in the previous in the literature on this. In particular, these two papers are, I think, most relevant: measurement robust CBFs and stochastic CBFs. The main difference with that in our work is in measurement robust CPFs, the key assumption is that the map C of X is invariable. They assume that you use some sort of camera system that can measure the true state at every given time, and that leads them to a SOCP type controller. In stochastic CPFs, they only design a controller that would be applicable to EKF type observers, extended common filter type observers, and they generate probabilistic safety guarantees. This work, we're assuming bounded disturbances and bounded measurement noise, and we're designing a system that could be for quite generic observers, as I'll go through in the next few slides. So that brings us to the next point, which is we are proposing two different solution approaches, and these two different approaches are based on the properties that are available to the observer. For instance, the first class of systems that we design is for input to state stable observers. Here we assume the estimation error is decreasing, and the bound is known a priori. However, we can also work with bounded error observers, where at any given time you know the set that the system lies in, but you don't know how it's going to evolve into the future, because that depends on the measurements that you receive online. Two different classes of systems have different properties, and we're going to be exploiting these different properties to be able to design our safe observer controllers. Let's start with the first start. In the first one, we say an observer is ISS if there exists a class KL function and a class K function that bound the error of the estimation error. Now, another way to put this, which makes it a little bit more easy to work with mathematically, is that suppose your initial error lied within some delta ball, then your norm error will lie within a m ball at all times. And m over here is a function of time that we know a priori. For an exponentially converging system, you would have some sort of exponential graph here. We're going to use this map m of t to be able to design our controllers. The key idea is quite simple. We're going to use the Lipschitz constant of h, and we say that if h of x hat is greater than gamma h of m, then you know that h of x is greater than 0. And so, given that this is a direct consequence of the Lipschitz continuity, we just need to be able to ensure that h of x hat remains greater than gamma h of m at all times. To do this, we take derivatives of h, and we can say that h is an observer robust CPF if it satisfies the following condition. LPH plus LQHU is greater than negative alpha of h minus gamma h m0, where P and Q again are from the observer dynamics. And if you have such an observer robust control barrier function, then it's quite easy to design a controller from there. The set of safe control inputs is such that LPH plus LQHU is greater than negative alpha h, and two extra terms here, minus gamma hm plus gamma hm dot. Now, let's parse these a little bit more carefully, but first we need to design these initial conditions. The initial conditions are pretty straightforward. The first one says that the x hat must lie within x hat 0, where x hat 0 is simply the set where h is greater than gamma h. It means that you start sufficiently inside the safe set, and x is such that the norm of x minus x hat is less than delta, which means you start sufficiently close to the true state. And so if you satisfy these two conditions and apply such a controller, then your system will remain safe. The two additional terms are quite interesting. Let's parse them a little bit more. The first term here is h dot, and the second term here is more conservative due to the current estimation error, right? We have to subtract a positive quantity over here. The second term here is plus a negative quantity, which means we are less conservative due to the decreasing estimation error, which means that if you knew the bound m dot, and you knew that it was decreasing, then you could use this to design controllers that are less conservative. There's a particular case that is kind of interesting and sheds some light on how this observer controller works. Let's consider a linear class K function alpha of r is just alpha r, and let's assume that our observer is exponentially convergent. In this case, you can simplify the algebra a little bit and show that LPH plus LQHU must be greater than negative alpha h, which is very similar to the standard CPF condition. The key property is that it doesn't depend on the Lipschitz constant gamma h. In fact, it also doesn't depend on the actual value of m. And what that means is that it matches with the general principle. The general principle being that if you want good performance, you should design observers to converge faster than controllers. You can see this quite directly from this construction on ISS observers. Next, we're going to talk about bounded error observers. And in bounded error observers, we're going to allow the shape and size of this to change over time. Over here, you can see that the size of the uncertainty is decreasing constantly in time, whereas over here, it's possible, especially at the end over here, that the size of the uncertainty set can grow. So let's define this a bit more formally. We say that an observer is a bounded error observer if there exists a set D and a set P, such that if you started within a D set of the true condition, if you started within a D set, you would remain within a P set for all time. In the diagram up here, the D set is the yellow set. As long as you start within the yellow set, we can construct this orange set P that you will always remain within. So we're going to introduce a theorem statement, and it's like a very straightforward feedback controller. If it satisfies this condition, your system will remain safe. Let's construct it together. We say that a controller is safe if pi lies within a set. The set is the intersection over all possible x's. So here we're taking an intersection over the p set of k-RCPF. And RCPF, the k-RCPF is the set of control inputs that are robustly safe. So the idea is really straightforward, right? If your system lies within the orange set at any given time, then applying a control input that is robustly safe for all such inputs is guaranteed to also be safe. And so this is like a really simple way to construct a control input that is going to be guaranteed to be safe. However, how can this be implemented? Right? We're taking this intersection of some set, and it's pretty difficult to implement in practice. So I'm going to introduce a simple method that reduces down to a QP. We're going to make some assumptions. The robust CPF condition is restated at the top over here. We're going to first take all of these red terms and we're going to bound it by some function a of t x hat. Second, we're going to assume that this LGHU term can also be bounded. In fact, the LGH term is lower and upper bounded by some b minus and some b plus functions. The key idea here is that we need to know how large a control input, that by applying a control input, what is the range of possible h dots that can happen. And one additional assumption we're going to make is that both b minus and b plus are of the same sign. The key idea here is that suppose we were applying a control input in the ith direction, so we're considering the LGH ith term. If the sign of it was the same, so if we knew that b minus and b plus were, let's say, both positive, then you know that by applying a positive control input in the ith dimension will lead to more safe behavior. If the signs were different, you wouldn't know which direction you should apply a control input in to be safe. So this assumption is, of course, fairly strong, but also fairly natural. While you're operating your system, you need to know which direction to apply a control input that would be more safe. And this leads to a really simple QP controller. The QP controller says, again, argmin of u minus a pi desired, subject to a plus min of b minus u, and b plus u must be greater than 0. And essentially that imposes this robust CPF condition subject to these assumptions 1 and 2. We're going to move on to the simulations. Here first we consider a double integrator, and here we don't even consider any measurement or disturbance noise. And the whole point of this example is to demonstrate why observer controllers are really necessary. So here we've got the position of the double integrator and the velocity. We're going to say that we have to stay to the left of this pink wall. So the true state of the system lies somewhere over here, so it's moving towards the wall at some relatively high speed. But our state estimate started out at 0, 0. We assumed it was at rest. If we apply the conditions for CVFs along the state estimate, you'll notice that the true state violates safety over here. And in addition, the state estimate also violates safety. And this is a really interesting effect, that even if we're applying a CPF controller on the state estimate, that both the state estimate and the true state could exit the same set. Using the two approaches that we've proposed in this paper, we'll see that both of them are able to lie within the safe regions at all times. Now, I've only shown you one particular instantiation of this that depends on the control input, the initial conditions, and I've played around with different initial conditions, and it's not entirely clear whether approach 1 or approach 2 are better. So I've currently left the paper as, I've left that point as future work. Second, we can consider a planar quadrotor system. So here we've got a quadrotor that starts over here, and the target is to reach a target point over here at 7 meters. But it is to avoid the obstacle that is in the middle over here. And what you see is that if you do a baseline controller, so a CBF controller on the state estimate, there is some violation over here. However, by using approach 2, where we bound this estimation error and design controls that are cognizant of it, the system is able to remain safe for the entire time. The key benefit here by using approach 2 is that, as you can see, that the covariance ellipsoid over here is shrinking as we go over here, but then it starts to grow again. And so that means that the state estimation error is not uniformly converging, and yet we're still able to maintain safety. Finally, we also implemented these experiments in a real quadrotor. So here we've got the quadrotor trying to fly a figure of 8 trajectory, and it knows about the barriers. It's trying to stop there, but as you can see, it did crash. So even though we have a control barrier function to prevent it from going into the wall, it still crashed because of the state estimation error. And here's our approach. It still tries to follow this figure of 8 trajectory, but it is aware of the barrier and it's aware of the state estimation error. Therefore, it doesn't crash into the barrier. It's able to complete the task safely. In summary, we've introduced two methods to be able to robustly handle state estimation error, and we've shown that it is really important to understand the behavior and the interplay between observers and controllers while we're designing safety critical systems. There's a few different experiments that we've done and a few different simulations. In the future, we want to relax the assumption that the safe side is known. That's a key assumption that we've been using so far. And this leads us to developing methods to construct these safe sets online and to construct them in a way that is certifiable as we're implementing our controllers. The second assumption that I really want to relax is this worst case disturbances assumption. While I've developed robust CPF methods, it'll be really important to be able to understand the impact of these estimation error bounds and try and learn them and try and reduce the size of these as we are operating in the environment. With that, thank you very much.